Hi, let's take a look at an example of calculating work from different forces. So for this example, we have a person trying to load a ballista. And a ballista is essentially a very large crossbow designed for shooting arrows the size of poles. So we could model a bow like a mass attached to a spring. And the spring constant for this ballista is going to be 630 newtons per meter. Now, it's designed so that as the person loading it pulls back, the person can apply a constant loading force of 340 newtons at an angle of 30 degrees above the horizon. And all of the change in motion happens very slowly, so essentially the system is never very far from being at rest. So our kinetic energy is going to remain unchanged throughout and practically zero. Well, as long as our kinetic energy stays the same, then the work energy theory says the total work has to be zero because our change in kinetic energy is zero. So if we take a look at all of the forces that could be there, well, gravity is acting on this object, pulling it straight down. There's a normal force supporting it, pushing it straight up if we're on horizontal ground. There's a spring force, there's the force of the loader, and there's very likely going to be some friction. Well, the neat thing with work is we can break out the work into the contribution from each individual piece. So if I start by looking at gravity, this person I've drawn loading everything, pulling to the left. So if my path element is to the left and the weight is straight down, there's a 90-degree angle between the force and the path, so gravity does no work here. Now for the normal force is perpendicular to the surface, so anytime an object is moving along a surface, the angle between that normal force from the surface and the object is going to be 90 degrees, so the normal force does no work here. Now, the spring, the loading force, and friction are going to do some work. So if we look at the spring force is pulling towards the right, trying to undo the stretch. The loader is moving to the left, so there's a 180-degree angle between the force and our path, so the work done by the spring would be minus 1/2 times the spring constant times the stretch of the spring squared. When we integrate the spring force, kx, with respect to x, we get that minus 1/2 kx squared. Again, the minus sign from the opposite directions. Now, when I plug in 630 newtons per meter and 0.85 meters for my distance, I get a work done by the spring of negative 227.6 joules. And as we'll talk about in a little bit, this work, negative work being done by a spring, is actually a store of energy that could be used later to put that projectile into motion. Now, the loader, we said, is applying a constant force of 340 newtons, an angle of 30 degrees along the path. So if the force is constant, then the work would just be the size of the force times the distance traveled times the cosine of the angle between the two. So I have 340 newtons times 0.85 meters times the cosine of 30 degrees gives me 250.3 joules. And they're in mostly the same direction. That's positive work. Well, if I add all of my works together, 0 plus 0 minus 227.6 plus 250.3 joules plus the work done by friction has to add up to 0. So that means then that the work done by friction is going to be minus the work done by the spring minus the work done by the loader. So I'd have 227.6 joules minus 250.3 joules. So the work done by friction would be negative 22.7 joules. And in Chapter 8, we'll talk about what this really means, but whenever friction does work, the energy that's being transferred is transferred from some useful force form into a less useful, less usable internal energy. Like I said, we'll dive deeper into that in Chapter 8. Now, if we wanted to extend this just a little bit farther and release it, well, if we were to ignore any friction on the release, then we could figure out the final speed of that projectile. So the final kinetic energy we could get would be minus the potential energy in the spring, because it would go from this negative potential energy to 0. 0 minus a negative number means that my final speed would be the square root of 2 times my energy divided by the mass of my projectile, which I set at 1 kilogram. So a 1 kilogram object being given 228 joules of kinetic energy would be traveling at 21.3 meters per second, which is about 48 miles per hour. Now, if we wanted to add in friction, we could make an assumption that, all right, well, maybe we have about 22.7 joules of friction or work also being done. So instead of 228, we'd have 205 joules of energy. And if we lower that a little bit, we lower our ultimate speed a little bit. But energy gives us a very powerful tool for investigating how kinematics works, as long as we're only caring about speeds and distances. Thanks for watching.